All right, so you guys can now jump into the platform yourselves. So turning back to the presentation, this first little lab exercise is just something for you guys to play around with the platform, basically doing a lot of the things that I just did. And it's pretty self-explanatory. Just walk through the steps and make sure you're comfortable with the environment. So I'll just give you a couple minutes to do that. You can pause the video. All right, we'll jump right into the next lab exercise. You guys can code up some simple combinational expressions, some logic gates, just as we were looking at. So again, this exercise is pretty self-explanatory, and I think I'll just let you guys pause the video and go ahead and read through it and do it. All right, next lab exercise, just going from Boolean logic, single-bit expressions, to operating on vectors. So in Verilog and TL-Verilog, which inherits expression syntax from Verilog, you can operate on vectors of bits as binary numbers. So I'll let you guys try coding an expression for an add. One thing I want to point out before you do that is, so in this expression, we've got explicit bit ranges on in1 and in2. Normally, on the right-hand side of an expression, it's not necessary to provide explicit bit ranges. Okay, you provide the explicit bit ranges on the signal that you're assigning, because that assignment is essentially acting as a definition for that signal. On the right-hand side, generally, you don't need to provide the bit ranges. That's already been defined for that signal. If you want to extract certain bits out of that bit vector, you can be explicit about the bits that you want. In this expression, I've had you be explicit because the in1 and in2, we're just leaving that up to the platform to invent input values for it. We don't have assignment statements for in1 and in2, and therefore we have no definition for what bits need to exist in in1 and in2. So we need to be explicit about the bits that we need in this expression so that the environment knows what bits to provide random stimulus for. So just want you to understand that. You need to be explicit here. In the future, on the right-hand side of expressions, if you're referring to the whole bit vector, the whole signal, it's not necessary to provide the bit range. And you can stop the video. Okay, so the next lab exercise is to code up a multiplexer, as we looked at before. So you can start out with just a single two-input single-bit multiplexer, and then you can modify that to operate on vectors of input and output bits. And I'll let you pause the video. All right, so now we're going to move on to something interesting and start to get into some real circuits that are doing well, interesting things. So in this example, we're going to code up a simple calculator. So our calculator will be able to perform addition, subtraction, multiplication, and division on two input vectors that are 32 bits each. So this depicts our circuit that we're going to implement. So basically we have our two input values and we're going to perform all of the operations on those two input values. Circuits, unlike programs, operate in parallel. We can, all of the logic in our design can be doing something all at the same time. So all of these resources are available to us. We just let them, in this case, we're letting each of them perform their computation and then saying, well, if that was the computation I wanted, take it, right? So we'll do the addition, we'll do the subtraction, we'll do the multiplication, we'll do the division, and then if the operation that we were requesting is addition, we'll select the sum. If it was subtraction, we'll select the difference, and so on. You can save power by only performing the operation that you need to perform, we're not going to worry about that. Sometimes power is an issue, sometimes it's not. You can often, as in this case, trade off power for performance. Okay, sorry, looking through the notes here. So just to note that your input values, val1 and val2, you can go ahead and use these expressions under item 2 here. And what that will do is, so rand1 and rand2 will not be assigned. And what MakerChip does, I think I mentioned this earlier in one of the labs, if you have an input that is not assigned, or a value, a signal that's not assigned, the MakerChip environment will just make up a value for that input. And here, we could have not bothered with these expressions and just let MakerChip come up with a value for val1 and val2, perfectly fine. The point of this expression is just to limit the range of val1 and val2 to smaller numbers. So rand1 and rand2 are 4 bits. We're going to get values between 0 and 15, or 0 and FF in hexadecimal. Sorry, 0 and F in hexadecimal. And then the assignment is going to 0 extend. So all the upper bits of val1 and 2 will be zeros. All right, and remember to save your project so you have something you can return to and bookmark it. And I'll let you guys use the syntax that you used in the earlier lab exercises to figure out how to implement this circuit. Multiply and divide we haven't looked at yet. I don't think we looked at subtraction either, but nonetheless, they're just like addition with either the minus operator, the asterisk, or the slash for divide. Okay, you can pause the video and take your time with that.